Now, let us try to calculate the power emitted per unit solid angle from the electric dipole radiation. But by the way, let me tell you something. This is valid for any kind of radiation in the far field zone. E is equal to h cross n. And the proportion of the constant is the, in magnitude, impedance of the space. So I shouldn't erase the magnetic field, I will need it. So what I'm going to do, calculate the power emitted per solid angle. That is related with the what? Pointing vector dot product with the surface vector. So since the fields are oscillating, we have an average 1/2. In general, the result should be real, but in that case, that will be real. R squared times n dot E H complex conjugate. So 1/2 E cross H complex conjugate is the vectorial quantity energy per second per area. The area element is nothing but the solid angle times the R square. And as I said earlier, E and H is going as a 1/r, cross product and dot product, whatever will be 1/r square, and the R squares will be cancelled out. That means that you can observe the radiation at any distant point, at the infinity. So let us find the expression first for the power emitted per solid angle. So electric field is Z0 H cross n, and you have what? That is equal to Z0 over 2 real part of R square n dot H cross n cross H complex conjugate. So switch the order, make minus. So then that will be what? H dot H complex conjugate, it will be H square. That will be along n, and that product with the n, that will be unity. H dot n will be 0. So this will give you a result Z0 over 2 R square H square. You can write the same thing with the electric field also. You can find the same result in terms of the electric field. So this is the power emitted per solid angle. But H square is going because 1/r square, and you have R square, that will cancel out. That means that the emitted power per solid angle could be observed at any distance. So for H at the far field zone, what was our H at the far field zone? That was C k square over 4 pi e to the I k r over r n cross p, I guess. So this is k square. This is the magnetic field at far field zone. You can calculate the E field also. If you plug this value, take the square, absolute square, you will end up what? E to the I k r magnitude 1. 1/r will be r square, and that will be cancelled this r square, and you will obtain Z0 over 2. R square terms will be cancelled out. Let me keep and cancel later. C square k to the 4 16 pi square n cross p over r square. So the important thing here, this power emitted per Solid angle again doesn't depend on r. Why? Because the r waves are spherical waves and that will be cancelled. So you can see that the radiation at any distant point, of course, if the medium is vacuum, not dispersed. So what is N cross P? N cross P geometrically is very simple. P is your electric dipole moment vector, N is what? Point of interest, and the angle is some theta, N cross P is sine theta. So basically power emitted per Solid angle will be Z0 32 pi square C square K to the 4, and depends on magnitude of the electric dipole moment and the angle. This is the angular distribution of the power emitted per Solid angle from the electric dipole radiation. What you need to calculate? Just the electric dipole moment. And if you have electric dipole moment P, the distribution of the radiation is something like this. Along the oscillation, along the oscillation, suppose that there is oscillating dipole in one dimension. So along the oscillation is, if you look at along the oscillation, so if the dipole oscillating to you, the angle will be 0, there is no radiation. And you can observe the radiation maximum at what? 90 degree. So it is called dipole because it depends on the dipolar form. So radiation is maximum here, 0 along the electric dipole moment, and symmetric in angle. So this is the form of the angular distribution of the electric dipole moment radiation. So if you want to calculate the total emitted power, you have to integrate through the Solid angle. And if you do this calculation, you will obtain something again related with the magnitude square of the electric dipole moment, and that something will be C square Z0 K to the 4 16 pi P square. So this is the power emitted per Solid angle from a dipole, and this is the total power, and both of them are related with the magnitude of the electric dipole moment. You can, or I can do a very quick example, a simple central FET antenna. So anything you know that the electric dipole moment, you can calculate the electric dipole moment radiation. But this is valid for a single dipole. If you have two dipoles, P1 and P2, you cannot apply this. Then you have to find that the electric field or H field at very far distances. Then you can use this. Okay. So if you have two antennas separated by a distance, you don't know that the electric dipole moment of the two antennas. If they are stuck together, you can calculate the total electric dipole moment. But if they are separated, you have to calculate the E and H and apply that at this. Because you know that at far field, so E and HN are related by what? E cross H0, H cross N. And this is a general formula for any kind of radiation in the radiating field. So let me do a quick example for the calculation of the electric dipole moment and the emitted power. So this typical example is the central FET antenna. So suppose that you have an antenna and you have an oscillating current. So the geometry is d over 2 and d over 2 up and down. This is the z-axis. So you have some oscillating current. So along Z, the oscillating current is something like this. It oscillates a single frequency, and the space part is 1 minus 2 over Z over D, oscillating in I omega t. What kind of function is this? At Z equal to 0, at the center, that is 0, when Z equal to D, Z equal to D, what is this? Z equal to D. So that should be D over 2. So at Z equal to D over 2, that will be vanish. Yes, that is something like this. Ez as a function of Z, and Z equal to 0, that is I0, and goes to 0 at the endpoints. So the only thing here, you have to calculate that the electric dipole moment of the antenna, just and then plug the formula here and find the power emitted radiation for the antenna and angular distribution. So how we can calculate the electric dipole moment? The electric dipole moment is the charge density x prime d cube x prime. In our case, x prime is the z prime axis, and we have to calculate the charge density. What we have is we have the current. So charge density and the current, or if you say that this is very tiny antenna, very tiny cross section, so you can calculate that the charge density and current charge density using the continuity equation. And since the fields are oscillating in the same frequency, that is nothing but del over del T minus I omega rho and divergence of J. So this goes to the other side as a minus, or keep it here. So J, our current density, is along the Z direction. So therefore this is equivalent to del over del Z of the derivative of this function through Z over D. They are oscillating in the same frequency. And if you take this to the other side, take the derivative, take the interior derivative, you have two options, positive and negative, because Z equal to 0 here and goes is positive here. So this is something like this is X, Y, and Z. When Z is positive, the derivative of interior will be positive. When the Z is negative, the derivative of the interior will be negative. And that means that the charge density in that form, I0 over omega D times a 2 factor. I think this should be correct. So take this to the other side, multiply it with minus. That goes. So take the derivative with positive. That will be negative. Goes to the other side is negative, and therefore multiplying with I, that will be the positive. So that is the correct. So when Z is greater than 0, this is plus. When Z is less than 0, that is negative. So then calculate that the electric dipole moment of the antenna and plug the result here. I can do this quickly. So I will use the final result. Let me keep the final result here. So the electric dipole moment, P, will be from minus d over 2 plus d over 2. Charge density is a step function. It's minus and goes to positive value, and x prime is z, and that should be taken through the z or z prime. You can put z prime or z, so that only represents the z. They are dummy indices, and you will get what? Rho is a constant, positive or negative, and if you take the integral, you will get rho z over z square over t, or z square d square over 2 d square over 4. So you will get z square over 2, put instead of z d over 2. Actually this should be d over 4. Z square is d square, and or let me write in that form: z square over 2 minus d over 2 plus d over 2. So if you take the positive range of this, you will get the plus sign of this. If you take the negative of this, you will get the negative of this. So altogether you will get plus rho over 2 d square over 4 minus for the lower one more minus because the charge density is minus value over 2 d square over 4, and altogether you will obtain rho d square over 4. This is the magnitude of the electric dipole moment, and if you plug here you will get the following result. So you will take this is the electric dipole moment, you will take the absolute value, absolute square of it, and plot here. You will get the following: c square z0 12 pi k to the 4. And what have you have? The square of this rho square magnitude is 4 I0 square omega square d square. This is the rho square magnitude. You have the rho, and you should have the square of this, and the square of that d to the 4 over 16. So I am just interested in with the orders. So you have d square and d to the 4. This makes d square. What is c square over omega square? 1 over k square. Okay. So this says the order some coefficient k square times d square. So 1 and 2 k square cancel because c square over omega square 1 over k square. This is k to the 4. That makes k square, and one of the d square cancels and ends in I0 square. So KD is a number. What kind of number? Since we are trading this antenna as dipole, and we are using the formula for the far field, so basically our wavelength is what? Is greater than the size of the antenna. So that tells you that d is the size and k is related to 1 over wavelength. This is a small number. Kd is a very small number, okay, because d is the size of the antenna, and at the far field the wavelength is not a far field, sorry about this, not a far field. In all our assumptions the wavelength is greater than the size of the source, okay. So that is the reason we are looking at the electric dipole moments and such things. We have the localized source and we are looking at the radiation at some distance further. So then this bunch here is what? So you have some numbers, some coefficients, and I0 square and emitted power. If you look at this using this some simple Ohm's law, what you see, power is related with the I square. I square is the current in the antenna. The rest of the stuff is what? What is the unit of the rest of the stuff? Resistance. So that is called as a, as you said, radiation reaction resistance. The name is radiation reaction resistance. The name is not important, but it's related a parameter with the resistance. So basically, we have to know that the electric dipole moment of the oscillating system in order to calculate the power emitted per solid angle or emitted total power. So now, I am trying to step to the next thing. Magnetic dipole moment radiation and electric quadrupole moment radiation. So I will start today, probably I will finish on Wednesday. So where we stop? We have a vector potential in terms of some series expansion, mu0 over 4 pi e to the ikr over r, and 0 to infinity minus ik over n factorial, current density, and dot x prime and d cube x prime. What I said, or what I did actually, not said, n equal to 0, that series could be written in terms of electric dipole moment. That was the starting point. So we said that when n equal to 0, the vector potential is what? Mu0 over 4 pi e to the ikr over r. This. And I think I show you that this is nothing but minus I omega electric dipole moment for n equal to 0 case. So that was the case for n equal to 0. Yes. Okay, I use the continuity equation and such things. I find the vector potential in that form. So if you look at the one higher order term, you will end up with the vector potential mu0 over 4 pi e to the ikr over r. When n equal to 1, that will be minus ik over 1. Current density and that x prime d cube x prime. So I will start here and I will play this term, and at the end, not today, you will see that this term could be a mixture of the magnetic dipole moment and the electric quadrupole moments. This term was related with the electric dipole moment, but this integral will be related with the magnetic dipole moment and electric quadrupole moment. That will be the first order. But in order to make the sum calculations easier in later, instead of using this expansion, I will use the exact expansion. Actually, this was the derivation for the far field zone initially. So what is our original vector potential? Let me write the vector potential in the original, and let me use the exact solution of the vector potential. This series expansion for the vector potential for the far field zone. So we have the vector potential mu0 over 4 pi current density x over x prime e to the I k x minus x prime e cube x prime. So this is the exact vector potential. And this is some assumptions. What are the assumptions? X is much greater than x prime, and the other assumption, the source dimensions is less than the wavelength. So the assumptions here, kx is a great number, kx prime is a small number. That was the thing. If you look at the notes, that was the consequence of these two expansions, the two assumptions. So I want to give you a tool. What is this? If you want to write that the exact solution or intermediate solution, let's say exact, you can have a tool of this e to the k x minus x prime or x minus x prime. Yes. You know that the expansion of this 1 over x minus x prime from the first part of the course in terms of the spherical harmonics. And there is one more expansion in terms of the spatial functions of that term. So that is given in your book. So I'm not going to derive. You can just look at the chapter 9 and equation 98. So that could be written in terms of Bessel functions and the spherical harmonics in that form. What I am trying to do, I am trying to write more general expression instead of this. Then I will use and do the calculation with that vector potential. So this is equal to L0 to infinity JL KR to the smaller HL. These are the Bessel functions and the Henkel functions. HL KR to the greater M minus L to plus L YLM complex conjugate theta prime phi prime. So I am not going to derive this. I will just use. So you have spherical harmonics and the Bessel functions. So this is a exact expansion of this term, but this is a very useful tool. So if you plug this information to here, you have to use what is what? R to the smaller and R to the greater. Basically, if you say this is x prime, this is the source region, x is much greater than x. So what is what? Do you remember what is what? What is R to the smaller and what is R to the greater? One of them should be R prime, the other should be the R. So you remember this from the last time. And if you take this and plug there, you will have the exact vector potential. So let me write quickly. I mu0 k summation through the L and M, L0 to infinity M minus L to plus L, HL KR, R to the greater should be the R, YLM theta phi, and R to the smaller should be R prime, therefore they should be stay with the integral. Current density X prime JL K R prime Y LM complex conjugate theta prime phi prime integrated through the volume. So at this point, just follow the simple calculation. So we will get a vector potential in that form. And just wait and see, in a moment we will get the result. You have a summation through the L and M. You know one tool, YLM, Y complex conjugate LM theta prime theta phi. If you sum this through the M, YLM theta phi, YLM complex conjugate theta phi prime is equal to 2L plus 1 over 4 pi PL cosine gamma. Gamma is the angle between N and N prime. N dot N prime. So if you have two vectors, what are these two vectors? X prime along N prime, X is along N. The angle between is N dot N prime. So this is another tool. So you know this tool from the first part. Gamma is the, let's say, the angle between the source and the point of interest. So if you plug this information to here, the vector potential could be written in the following form. So let me tell you again, I am not doing anything fancy. I am just using one definition of the very nice formula. E to the ak x minus x divided by x minus x prime could be written in terms of some spatial functions. When I plug here, I will find that the exact form of the vector potential, and one particular case, L equal to 1, will give better expression than this. Okay, so today I will carry with that point, and I will work to study for the magnetic dipole moment and the electric quadrupole moment radiation next time. So a few steps is enough to see what is going to happen. I mu 0 k summation through the L and M. Not LMM, the M is summed here. I summed the M here, and I get that the 2L plus 1 over 4 pi 2L n dot n prime. So summation through the L, 2L plus 1 over 4 pi HL KR, current density JL, Bessel function, spherical Bessel function, KR prime times PL n dot n prime to cube x prime. Again, let me tell you that n prime. N prime is the direction in terms of the theta prime, phi prime, and n is the direction in terms of theta and phi. N dot n prime is the angle between them. N prime is physically source location along the unit vector along the source location, n is the unit vector along the point of observation. So this is the form of the vector potential. Specific case is what? L equal to 1. will be the following. For a specific case, okay, I don't find at this point. For that part, take the L equal to 1. Where is there's one more term is missing? Which term is missing? So I confused. 2L plus 1. Oh, it is there. Okay, okay. Put L equal to 1. Then for specific case, A will be what? When you put L equal to 1, that should be 3. 3 mu 0 I k over 4 pi. H1. This will be the H1. And H1, when L equal to 1, what is the condition for Kr? Kr is a great number, Kx prime. Okay, there's a asymptotic form of the Bessel function. Look at the section related in chapter 9. So there's a very nice chapter summarize the forms of the Bessel functions and gives this as a nice tool for you. So for Kr, so that is equal to e to the minus e Kr over Kr 1 plus I over Kr. So this is the asymptotic form for h equal to 1 when Kr is greater than 1. So basically L here is 1. L is equal to 1. For the source region, Kr prime is a small number, and there's another asymptotic form of the Bessel function. Kr prime is a small number, then this could be expressed as a 1 over 3 Kx prime or r prime. Okay, I am leaving as a x prime because I have the integral here. So we will come very quickly to the end. When L equal to 1, what is the P1? Do you remember P1? What is the Legendre polynomial order 1 P1? Not 1, it's 0 and it's 1, so that should is the what? Cosine theta. Basically, this is nothing but, what is this? This is nothing but n dot n prime. N dot n prime is the cosine gamma. Okay, so that's all. Now I will just write the result. I will just write the result. What is this? Okay, so I'll erase this and write the result. So I don't want to spend much more time here because we come to the end. For L equal to 1, this is 3. Cancel this 3. Okay. And the result is the following. Mu 0 over 4 pi. You have e to the Kr over Kr. Actually, that should be positive. I miswrite the asymptotic form. This should be positive. The overall is negative, okay? E to the kr over r, that is a spherical wave term. So that will be e to the ikr over r, 1 over r minus ik. This should be the coefficient part. You have I, you will distribute inside, that one term will be minus, and this will be minus, and the other will be the I. So if you arrange terms, you will get this. And the other term, current density here, you have. And you have what else? K. So one of the k's will be cancelled. You have the k square here and 1 over k, that will be cancelled. So don't worry about this. And you have x prime n hat, x prime n hat is the x vector. So basically you will get this. So I know that you lost to keep track, but let us look at the integrand first. Let us look at the integrand here. You have x prime, n prime, this is x prime. Okay, x prime vector. You have n hat, you have the current density. Is this term is here? Yes. Exactly identical. If you play the coefficients, don't worry about this. If you play the coefficients, you will get this. You have 3 and 3 will be cancelled. You have k and k, one of the k cancel, distribute the ik inside, and you will get this. So this is guaranteed. You look at these steps, you will find very easily. But the only difference between this term and that term is what? What is the difference between these two coefficients? What is the? They are not exact, but almost exact. What is the difference? There is a spherical term. This term is the spherical, but you have 1 over r here, extra term here. So that extra term is helpful in our calculations with the symmetric point of the magnetic field. When we calculate the magnetic field, we will get a very symmetric expression, which I did in the first hour for the electric field. So I will explain this when I come to that point. But in the far field, this expression and that expression identical because this doesn't contribute. But I try to include this term by taking the general expression, pumping to here. I know that what is going to end. So what is going to end? I know that I will need B as a curl of E, and I will see that very symmetric. When I calculate this term, I will find that the magnetic dipole moment term is very similar to the electric dipole moment, and the calculation will be very, very easy. So at this point, I cannot tell more, but next time, when we calculate that the radiation for the magnetic dipole moment, we will see that why we needed this term. So wait and see to the next time. But so far, both approaches the same in the far field. Only this has the, as you said, non-spheric wave term is going as a 1 over r square. Okay. So that's why I don't want to spend on time this derivation. This derivation could be nice for the mathematical purposes, but for this course, for that purpose, it's not very, very important. So what I needed, this expression, and it says the only additional term is 1 over r. So next time, I'll calculate the magnetic dipole radiation and electric quadrupole radiation. And next week, I will start the multiple expansion of the radiating fields.